Hi everybody. Hope you're all having a good day today so far. Today we're going to talk about binary relations. And we'll start with a couple of definitions, and then we'll do some examples of binary relations, and we'll look at the properties, several important properties of binary relations. So, binary relations. What's a binary relation? Well, a binary relation is just nothing but a subset of a cross product of two sets. So, for example, if we have a relation between the members of a set X and a set Y, then the binary relation is a subset of X cross Y. In other words, it's just a set of ordered pairs where the first component of the pair is always drawn from the set X and the second component is drawn from the set Y. So we would write XY is an element of R if R is the name of the relation, which is a subset of X cross Y. We would write the ordered pair XY as an element of R, but we typically also write, in fact it's more common to write, instead of writing the ordered pair as an element of R, instead writing X, R, Y, which is just a synonym for the ordered pair being an element of R. So to say this is the same as saying this, X, R, Y. We would say X is R related to Y, or simply X is related to Y. So let's start off with several examples of relations. Our first example, we're going to have the set X be a set of students, and the set Y will be a set of courses that the students might be taking. So this could be an economics course, a math course, a history course, maybe several different economics courses, math courses, and so on. So it's just some set of courses. And we will name our relation, our first example of a relation, we'll name it R for relation. And so we'll say here, XRY means that the student X is in course Y, taking course Y. In fact, we could even say that R stands for registered in. So student X is registered, let's say, in course Y. We could have another relation, say, a different relation called C, that student X has completed course Y. Now, we might expect, at least typically, so let's write typically here, because I want to emphasize this isn't necessarily the case. Typically, we might expect that the relation R and the relation C are disjoint. That is, there's no student who's both registered in a given course and also has completed the course. So we might expect this to be the empty set. Now, again, that doesn't have to be the case, but we might expect that typically to be the case. And I'm writing that only to emphasize, it's not because we're going to use this, I'm only writing this to emphasize that the relations R and C are subsets of, they're both subsets of X cross Y. They're sets. And so the fact that they're sets makes it sensible to be talking about the intersection of the sets, and perhaps a set being an empty set. What about another relation? Let's suppose that we have the relation L. And let's say that XLY means that student X likes course Y. So let's say that. And here we might imagine that, in some cases at least, that the students have registered and are taking exactly the courses they like. So it might be the case that, for example, that L, the relation or set L, is equal to the relation R, that students have registered in exactly the courses they like. Or perhaps that L is equal to R union C. That is, that the courses the students like are exactly the courses they're in, or registered in, or have already completed, and those are the courses they like. Again, that's not necessarily the case, but we might imagine that it could be the case. Again, I'm writing this to emphasize these are sets, but here I have another motivation for writing this, and that is that let's suppose these are equal. Conceptually, a student liking a course is not the same as being registered in the course or having completed in the course. They're different concepts, they're different ideas. So the relations wouldn't have to be the same, but they could be the same. And in fact, here, let me take off the union because I want to emphasize. So let's just suppose the students are registered in the courses they like. Maybe the courses they've completed they don't like, okay? So here, the fact that liking the course isn't really the same as being in the course or registered for the course, but the fact that the relations are the same, coincidentally, the students like the courses they're registered in, makes these the same relation, even though they have different names, conceptually they're different, they're the same sets, the same subsets of the product, the cross product X cross Y. And let's do one last example here with one last version of our example with students and courses. Let's look at the relation F, another subset of X cross Y. Let's suppose that XFY means that student X failed course Y. And so let's suppose that for the particular set of students we have and the particular set of courses we have, let's suppose that none of these students has failed any of these courses. So then we would have the relation F, again a subset of X cross Y, would be the empty set, just like the empty set up here. Again, the empty set, perfectly good subset of X cross Y, so it's a perfectly good relation because relations are simply subsets of the cross product of the X set and the Y set. So now I'm going to take this example off, and then I'm going to go through several other examples. Okay, for our second example here, we're going to say, let's suppose that we have some function from a set X to a set Y. In fact, this will draw a picture down here. Let's suppose this is our set X, and this is our set Y, and we have a function that goes over from X to Y. And we're going to define a relation not between the members of X and the members of Y in this example, but a relation between the members of just the domain, the set X. And in fact, most of the relations we're going to deal with today, and most of the relations we deal with in economics, I guess I would say, are relations like this. So they are relations between members of the same set. We sometimes say a relation on X for that. And so our relation here is going to be defined by saying that X R, and let's say X prime, I don't want to use Y right now because I want to emphasize that both elements come from X, not from the Y set. So X R X prime means that f of X is equal to f of X prime. So two elements of the domain are related in this relation if they get mapped to the same element in the target space. So that would be a situation like here we have an X that goes over to some element Y, let's say, and then we have maybe another element X prime in the domain that gets mapped to the same Y, the same element of y. And let's notice that there are several characteristics or properties of this specific relation that we've defined that are kind of interesting, and in fact they're going to turn out to be pretty important. So the first property is that for every element of the domain, for every element of x, it is the case that x are x. That is, the ordered pair x comma x, and in fact let me write that down here just to emphasize that, the ordered pair x, which is an element of x cross x, that ordered pair is in the relation because f of x equals f of x, and that's true for every element in the domain. So every element in here. A second property of this particular relation we've defined is that for any two elements of the domain, x and x prime, if x is related to x prime, then it has to follow that x prime is related to x. And that's because, of course, if f of x equals f of x prime equals f of x. So that's straightforward. And a third property that this relation has, for every x, x prime, and x double prime in x, it is the case that x are related to x prime. Whoops, we don't want that. So let's take that off. And x prime are related to x double prime implies that x is r related to x double prime. And of course, that's just because if we have f of x equals f of x prime, and f of x prime equals f of x double prime, well then all three elements of the domain, x, x prime, and x double prime, are all getting mapped to the same element of y. So f of x is certainly the same element of y as f of x double prime. So each of these three properties turns out to be extremely important, and we're going to come back and talk about those properties in just a few moments. Let's do another example. Let's suppose again that we have a function. This function we're going to name u, and this function is some set x into the reals. So it's a real valued function on a domain capital X. And let's suppose that this function is a function describing the preferences of some decision maker who has to choose one of the elements of x. So we'll think of this as a utility function, and that's why I use u. So the elements of x are some alternatives that our decision maker has to choose from amongst. They could be a set of possible actions that he has to take, a set of consumption bundles that she might purchase, has to choose one consumption bundle. Could be a set of candidates that one wants to vote for one of the candidates. Could be a set of policies we have to choose, and so on. So the U describes our decision maker's preference among the various alternatives, and we could say it describes that in the following sense. Let's say U of x is bigger than U of x prime means that our decision maker prefers x to x prime. So I've got a given utility function, a given function, and I'm now defining a preference called P, an order named P that we would refer to as a preference or preference order. So this is a binary relation. The x and x prime are both members of the domain, the set of alternatives the individual is going to choose from amongst, and we would just say x is preferred to x prime, and that's our interpretation of u of x being bigger than u of x prime. And we also alternatively write this with this sort of curvy greater than symbol. That's a kind of standard symbol that we use for strict preference. The person prefers the alternative x to the alternative x prime. And then if u of x is equal to u of x prime, we'll interpret that to mean the decision maker is indifferent between x and x prime. And we are defining now a different relation. P is this preference relation. I is now an indifference relation. And we would typically write that this way as an alternative perhaps to using I. So in a sense, I've got two different symbols now for the same exact relation. P, or this curly greater than, I, or this little tilde. And finally, let's say if u of x is greater than or equal to x prime, if u of x is greater than or equal to u of x prime, we'll write that as x r x prime, and the alternative notation we'll use for that will be combining the curly greater than symbol with the little tilde. And so here you'll notice how similar this is to a fourth example that we're all familiar with, the relations greater than and equals and greater than or equal to on the set of real numbers. So these are, all three of these are relations on the real numbers. That is, each one is a subset of R cross R. And you can see the similarity, and even conceptually similar, to our three relations here, but they're not identical in general. And we're going to come back and compare these and talk about them in a few moments. And let's look at a fifth set of relations here. And then we'll go on to lay out several of the properties of relations and see how our examples fit with those properties. So here, I'm going to say X is a set of people, some set of people. And I'm going to define several relations on X. That is, several relations between the members of X, between the people. The first relation we're going to define is, and here I'll use X and Y, even though there's no Y set here. We're just talking about subsets of X cross X. So I'll say that X and Y, if person X lives next door to person Y, if they live next door to one another, then they're in this relation. Again, we could write this, of course, as XY is an element of the set N, which is a subset of X cross X. A second relation. Let's say X lives on the same block as Y. So let's just say they live on the same block. A third relation. Let's say the relation S is X is a sister of Y. Another one, let's say X is a daughter of Y. And let's do one more. Let's say the relation A, X is an ancestor of Y. So this is not going to be part of a cognitive test where you have to remember next door, same block, sister, daughter, ancestor, like person, woman, man, camera, TV. But we are going to look at each of these five, a kind of cognitive mistake there. There's 5 of these relations. We're going to look at each of these 5 relations, and we're going to consider several different properties of the relations and how they are similar or different from one another.